Hi everybody, this is Dr. Tausman. I'm going to record the correlation and regression lectures that we'll also cover next week. The idea is take good notes on this information and come into class next week with questions if you can. So I'm going to start following the agenda here with an example with sleep apnea. If you follow the example, you can see I take 5 people and I measure their BMI, and I also know how many snoring episodes they have during the evening. If you know anything about sleep apnea, you know that you can measure sleep apnea by snoring episodes. So, and BMI, of course, is a weight index. And one of the ideas behind this information is that the higher your weight, the more likely you are to have sleep apnea. So I do a study. I wouldn't normally just collect 5 people, but for the sake of example, I'm going to say that's the case here. So if you look at these 5 people, going across each row, we start with a BMI of 30 and go up to a BMI of 40. And if you look at the snoring episodes, it looks as if for these 5 people, as the BMI increases across these 5 people, it looks like the number of snoring episodes also increases. So going down to part B, how is this data different than the other data sets we've had this semester? The key answer to that has to do with the nature of the data. These two variables are what we call continuous variables. Continuous variables can range according to a whole sort of number of values. In other examples, like when we were doing a t-test, you had to have one variable that had to have 2 levels, and that was the independent variable, and a dependent that could be continuous. So this data, both variables have to be continuous to do a correlation. In previous examples, one variable was categorical, meaning it had to be this category or that, and the other one was continuous. To run a correlation, most of the time both variables can be continuous. The other key here with this example is you notice I'm not manipulating any variable. So when you run correlations, you can just collect data and you don't necessarily have to manipulate variables. So that's how this data set is a little bit different. If you go down to C, the visual representation, many times the way we look at data when we're looking at correlation information, we make a scatter plot. And if you take a look at the scatter plot, you can see I've basically plotted out the BMI on the x-axis and the snoring episodes on the y. So can you see where I've got the 30 and the 10, and then I've got 32 and 15, and then I've got 35 and 25 snoring episodes, and then 38 and 40, and then the final one is 40 for the BMI, and they have snoring episodes 80 during the evening. So the way we make out charts for correlations is we make a scatter plot, and you can see it clearly here. So that's how we do the charts. The other thing that we do with correlations is what kind of correlations do we get? Well, we can actually look at that with C here. When we do correlations, correlations can range anywhere from +1 to -1. Now, if you look at this data and you go across BMI and snoring episodes, it looks very obvious that as BMI increases, so do the number of snoring episodes. So we would expect a positive correlation approaching +1 here. And if you look at C, the correlation results, you can actually see that the correlation is 0.915. Positive, the sign matters here, positive 0.915. And you'll notice that it has a little star above it, because if you look under the 0.915, you can see that the probability of getting this correlation due to chance will be 2.9% of the time. So this correlation would be considered statistically significant, that there does look like a significant relationship, and the real-world statement would be that as BMI increases, so do snoring episodes. Snoring episodes are our operational definition of sleep apnea. So as BMI increases, so do snoring episodes. It's a significant relationship, and it's a positive correlation. If you need an example of a negative correlation, what if we looked at, what would be a good example? What if we measured temperature on 5 given days and we looked at the number of parkas bought at a winter shop? So as temperature increases, the number of parkas purchased would go down. So as one variable increases, the other one decreases. That would be a negative correlation. It would probably be a significant one as well. So correlations can range, and you can look at this in your book chapter. I think it's chapter 15 or 16. That as one variable increases, so does the other one. A negative correlation can be equally as strong as one variable increases, the other one decreases. The type of correlation we don't want to get is one close to zero. So if you get a correlation close to zero, that basically means that there is no relationship between the two variables. The way we would write up this particular correlation is we would write the letter R, and then in parentheses you have to have degrees of freedom. To get degrees of freedom, you need to take the number of pairs and subtract 2. Not just 1, but 2. So it'd be R, little r, parentheses 3 equals positive 0.915, and then P equals 0.029. And the real world statement, as BMI increases, so do the number of snoring episodes. So hopefully that makes sense for you. Let's see if I want to go in the next example. I'll put it on a new recording here. Thank you.